This is lecture 2 for module 4 in the book Problem-Solving Guide for Electromagnetism and Optics on capacitors. Here we're going to start with two parallel capacitors with a battery. We'll call this one C1. Call the middle one C2. There's a battery on the bottom. What's going to happen here? The battery does the same thing it always does. It shuttles charge from one side to the other until the potential difference between any point on one side and the other side is the voltage of the battery. So we'll look up the battery, label some points on the diagram, and quiz you. Yes, you. Pay attention. Here we go. Here are the points: A, B, C, D, and E. I'm going to take a voltmeter, hook up the red lead to one point, hook up the black lead to the other point, and read what says on the voltmeter. Let's assume the battery voltage is 20 volts. What's the voltage difference between points A and B? A and B are hooked up directly across the battery. It's 20 volts. How about A and C? It's 20 volts. A and D? 0. If you take a charge from here to here through the wire, the charge does not speed up, does not slow down. Level ground here, it doesn't go across the capacitor. C and D, that's 20 volts. D and E, that's 20 volts, the voltage of the battery. C and E, 0. A and E, 20 volts. Okay, what's the voltage drop across this capacitor? It's 20 volts. What's the voltage drop across this capacitor? It's 20 volts, the voltage of the battery. Each capacitor is connected directly across the batteries. The battery can charge each capacitor independently. The charge C1 gets is completely independent of how big this capacitor is. The charge this one gets is C1 times the voltage of the battery. This could be a big capacitance, it could be a small capacitance, doesn't matter. C1 gets the same charge all the time. And that charge is C1 times V, the voltage of the battery. Each capacitor gets the full charge. If you want to store a lot of charge, this is how to hook up capacitors. So let's determine the equivalent capacitance of two capacitors hooked up in parallel, like this. C equivalent is Q over V, where Q is the charge to the battery, V is the voltage of the battery. But here, the charge to the battery is the charge this one gets plus the charge this one gets. Q1 plus Q2. The charge that goes through the battery gets split up. Some of it goes here, some of it goes here. For the individual capacitors, C1 is Q1 over V1, C2 is Q2 over V2, but here the voltage drops are the voltage of the battery. We don't need subscripts on the voltages. They're all hooked up across the battery. So C equivalent is Q through the battery divided by the voltage of the battery. The charge through the battery is Q1 plus Q2 over V. I can separate these two like that, and it's just, that's C1, that's C2. So C equivalent is the sum. Of course it is. It should make sense. You can store charge on this one, you can store charge on that one. The total charge you can store is the sum. So now let's put some numbers in to see how it works. Battery's 20 volts. We'll call this capacitance 20 microfarads, this capacitance 30 microfarads, like that. Hook up the battery. What happens? We're going to calculate the charge shuttled through the battery two different ways. First, we're going to treat the capacitors individually, then we're going to get the equivalent capacitance of the circuit. This capacitor has 20 volts across it. It gets 400 microcoulombs of charge. Q1 is C1 V1. V1 is the voltage of the battery, which is 20 volts. There's the capacitance. I know this guy gets 400 microcoulombs of charge. And there it is. The 30 is also hooked up across the battery. It gets 600 microcoulombs of charge. Therefore, the charge that went through the battery is 1,000. 600 of it's here, 400 of it's here. The battery sucked 1,000 microcoulombs of electrons off of these two plates and stuck them over here. Now let's use the equivalent capacitance. So what does the battery think is up there? The battery thinks there's a 50. C equivalent is C1 plus C2. The battery says, okay, there's a 50 microfarad capacitor up there. I'm a 20 volt battery. How much charge do I shuttle through? And the answer is 1,000. There's the capacitance of the whole circuit. There's the voltage of the battery. And this is what we got before when we did it individually. It's all consistent. It all makes sense. So the value of a capacitor is directly proportional to the area of the plates. The battery has access to this area plus that area. The equivalent capacitance is the capacitance of this plus the capacitance of that. You can connect these two sides by wires, and it would be exactly the same. C equivalent is C1 plus C2 when capacitors are in parallel. So you're saying, why would anybody use capacitors in series when you get less capacitance? And the answer is, one reason is to protect them from burning out due to high voltage. So let's see how that works. If the voltage gets too high, the charge is going to jump across the gap. And something's going to smell. It's breakdown. It's no good anymore. It burned out. I smell something burning. Since the capacitors in series, one after another, share the voltage of the battery, a higher voltage can be placed across both of them than two in parallel. So let's consider a circuit. Each capacitor has a capacitance of 60 microfarads and a breakdown voltage of 50 volts. So if the voltage across the capacitor gets to 50 volts, the charge is jumping across, and you're going to smell smoke. So what's the breakdown potential of this circuit? Each of these capacitors is 60 microfarads. Each will break down when it gets to 50 volts. I have a power supply here indicated by this arrow, a variable power supply, and I'm cranking it up. I start at 0 and I turn it up. 10 volts, 20 volts, 25 volts. Anything smell yet? Not yet. 30 volts, 35. When is it going to start to smell? When is one of those capacitors going to get to 50 volts? You got it? It's 50 volts. Each capacitor has the voltage of the battery. When the power supply gets to 50 volts, each capacitor is at 50 volts, and they both start to smell at the same time. How about this circuit? Two capacitors in series across a power supply. I start to crank up the voltage, 10, 20, 30, 40. Anything smell yet? When I get to 40, what's the voltage across each capacitor? It's only 20. Each capacitor has a voltage drop of 20 across it. The capacitors protect each other from high voltages. The breakdown potential of this circuit is 100. When I get to 100, each of these will be 50, and they'll both start to smell simultaneously. When they have the same capacitance, it's relatively straightforward. But let's consider a circuit of two capacitors in series in which they have different capacitances. What's going to happen here? One's 30, one's 60. Like this. Which of these two capacitors gets more charge? It's the same. They're in series. They can't possibly get different charges. Since they have the same charge, the smaller capacitor, the charge is going to be jammed closer together. The field's going to be bigger. The voltage drop across this one is higher than the voltage drop across this one. So this is the vulnerable one. This guy's burning out. This guy's not burning out. This guy's going to burn out before this one. And when this one gets to 50, it's going to burn out. This one's not even going to be 50 when this one gets to 50 volts. When this one gets to 50, the voltage drop across this one is going to be only 25. It's got twice the capacitance. So the breakdown potential of the circuit is 75 volts. If I crank this up slowly, when it gets to 75, this one's going to get to 50 and hence start to smoke. The 30 is going to break down. The 60 won't break down. So let's think about this. The battery only has access to the left side of the 30, the right side of the 60. It shuttles charge through it. The charge on this one has to be the charge on that one. And then you have this transfer of charge in the middle piece. Charge must be the same. Now let's look at the voltage drops. We know that C is Q over V for each individual capacitor. We know the charge is the same. The capacitance is twice as big. The 60 has a big capacitance. The voltage is the charge divided by the capacitance. The charge is the same. The voltage across the 30 is Q over 30. The voltage drop across the 60 is Q over 60. This is smaller by a factor of 2. The voltage drop across the 30 is always twice the voltage drop across the 60 because they must have the same charge. They're in series. When the 30 microfarad capacitor has a voltage drop of 50 volts across it, it has a charge of 1500. And 1500 must be the charge that went through the battery. So 1500 microcoulombs was taken from this side and put on this side, and this one's going to start to smoke. The 60 must have a charge of 1500 divided by the 60 microfarads. It's got a voltage of 25 volts. That's 50. That's 25. The power supply reads 75. That's consistent with what we had before. Now let's do the same calculation with the equivalent capacitance. What capacitance does the battery think is up here? We have a 30 and a 60 in series. This is the formula. We can plug it in the numbers. C equivalent is 1 over C1 plus 1 over C2. 1 over 30 plus 1 over 60. 1 over 30 is 2 over 60. Get a common denominator. 2 60ths plus 1 60th is 3 60ths. 3 60ths is the same as 1 20th, which makes C equivalent 20 microfarads. So the battery thinks there's a 20 microfarad capacitor up here. When the power supply gets to 75, which is when this burns out, the charge shuttled through the power supply from one side to the other is the equivalent capacitance times the voltage. 20 times 75 is 1500 microcoulombs, and that's the charge we got on these two capacitors when the circuit burned out. Same result. There's one more subject to cover for this module, and that's dielectrics, a material that you can stick in between the plates of a capacitor to increase the capacitance. Dielectric polarizes in the presence of the electric field. It's non-conducting, so the charges can't go long distances, but they can lean one way. So you can increase the capacitance of a capacitor for a given geometry. Let's see how this works. The capacitance of the capacitor is Q over V. Same equation we always had. What we want to do is reduce the voltage drop to make the capacitance bigger. If we reduce the denominator, C gets bigger. The voltage drop is the electric field divided by the distance between the plates. There's my big capacitor. We want to decrease the voltage drop without changing the geometry. We have to reduce the electric field. With the charge separation, there's a certain electric field, like this. So here are the field lines. We want to decrease the field without decreasing the charge. We want to store a lot of charge, but we don't want the field to be big. How do we do that? It's a pretty good idea. Let's put a dielectric in there and see what happens. If you put a dielectric in there, this positive charge is going to attract the negative charges. They're not going to be able to travel long distances, but they're going to lean. So this side is going to be negative. This side is going to be positive, like that. And what happens is the field lines end. They go from the positive charge to the negative charge, and they end. and the field begins again at this positive charge and makes it over to the negative charge. Some of the field lines make it all the way through. Some of the field lines end on the negative charge, and you see that the field inside the dielectric is reduced. We reduce the field between the plates without reducing the charge on the plates. And if we take a positive charge from this side to that side, it's going to get less energy, which means the voltage is less. So we increase the capacitance by reducing the field for the same charge. Now we have a bigger capacitor. The factor by which a dielectric increased the capacitance is simply the dielectric constant of the material, which is epsilon. So we have the original capacitance, C naught, and then we have the dielectric, and then we have the new capacitance. It's just simply a multiplication factor. If we stick a dielectric in there, it's going to reduce the field. So field lines end right away, and they start here and make it all the way across. Some of the field lines go all the way through. So the field is reduced, the voltage is reduced. If the dielectric constant is 2, the capacitance doubles. If the dielectric constant is 2.5, and we stick it in between the plates of a 60 microfarad capacitor, the capacitance is now 2.5 what it was, which is 150 microfarads. That's all the material in Module 4. Now you have to practice and solve problems with complicated circuits, try to figure out where the charge is going. Get to work.